Good afternoon, class. Today what we're going to be looking at are circles. In fact, that's what this entire chapter is about. In particular, we're going to use a few properties of what we call tangents. Now, there are a few new things in the circle that we need to learn about, and that's where we're going to start. So in this section here, the first thing is the parts of the circle. If you look, there's three parts that you probably already know about. We call them the center, the radius, and the diameter. The center is the point in the middle of a circle, so it would be this point right here. The center is the same distance or equidistance from the edge of the circle. That segment from the center of the circle to the edge, here in blue, is what we call the radius. There's any segment from the center to the edge of the circle is a radius, even if I don't have it drawn. And a diameter is what we call a chord. A chord means it goes from edge to edge of a circle. This chord just happens to pass through the center of the circle. So it goes from one edge to the other, but it goes straight through the middle. So it goes through the center. So those are the three shapes you already knew. The three shapes you didn't is, first of all, that chord. A chord is a segment that goes from one edge to another edge. A secant is like a chord, but it actually goes through the circle at more than one spot. And I realize I forgot to change one of the words here. The chord is the segment here in red. It goes from edge to edge. It doesn't have to go through the center. If it does, we call it a diameter. The secant is this blue line up here. It goes through the circle at two different points, and it goes on forever in either direction. It's secant. It crosses the circle twice. I know it says radius, but it's supposed to say secant. I mislabeled it. Sorry. Down here, this one that touches the circle only once is what we call a tangent. It touches only once. So these are the three new shapes. There's actually a fourth one, and that's just where the tangent line touches the circle. There's a point there that we call the point of tangency. It's just letting me know that that's the point that the tangent line crosses the circle. Alright, so these are the different parts of a circle. The first type of question you might see is match the notation with the term that best describes it. So for instance, if I'm looking for segment AB, I'm going to look segment AB. Well, point A there looks like the center. You might try and argue that point F here is the center, but it isn't. It's point A. Point A marks the center. Point F marks this intersection. So point A to point B, that's from the center to the edge of the circle. Center to the edge, that's a radius. The first one's a radius. 2 is segment BH. So it's a segment. Doesn't go on forever. It goes from B here, edge of the circle, to H here, edge of the circle. Segment BH, from one edge to another, at least a chord. At least a chord. Does it go through the center? No. So it's only a chord. 2 is a chord. 1 is radius, 2 is a chord. 3, line DB. D and B are both on the edge of the circle. And this line goes through both parts of the circle. That there, because it goes through two parts of the circle, is what we call a secant. Mr. H, it goes through the center. It does, but there's not a special name for it. It's just the secant, because it's a line and it goes through the circle at 2 points. Secant. And segment EG, E is here, G is there. Sorry, line EG. This line crosses the circle at point E. It's the only part it touches the circle. Line EG is a tangent. So 1, radius. 2, chord. 3, secant. 4, tangent. 5, it says name the circle with notation. It's circle A. Now if I'm going to use notation, there's two ways I can name it. I can either call it circle A this way, or I can simplify it circle A. And there we go. That's everything for example 1. Just naming the parts. Relatively nice to us. Example 2, we take it a little bit further. And we're going to say, how can circles intersect? Well, there's 5 ways for them to intersect. But there's only 3 different types of intersections. So, two circles can intersect in 5 main ways shown below. Concentric circles are circles with the same center. So if I look here, this leftmost part, two circles with two intersections, it's going to look like a Venn diagram. No matter if the one circle is bigger or smaller, it's going to intersect twice. That's how it would look. For the ones with one intersection, I could have the circle on the inside and one circle on the outside, and they cross right here. It's going to look like a crescent moon. Another way is if the two circles are right next to each other, they could touch once, just barely touching. Sort of like this ideal. This bottom of a battery is a circle, this bottom of a battery is a circle, and they're touching right next to each other. These two would be two circles that have 1 point of intersection. Tangent circles, by the way. And the last case is no points of intersection. They're like this, where they have no points of intersection, they're just apart, or it's like a target where a circle is outside of another circle, which is outside of another circle. They don't have to have the same center, but they could. Alright, so those are the different types of intersections for a circle. The reason we look at these is so we can talk about another thing about tangents. We're looking at tangents mainly today. So talking about intersection of circles almost seems off track, but because we're going to talk about what it means to be a common tangent, we need to talk about this first. So, a common tangent is a tangent line, ray, or segment that is tangent to multiple circles. It doesn't have to be just two, it could be 3 or 4, but the only cases we're going to look at are 2. So what it means to be a tangent or a common tangent is it's tangent to the left circle and tangent to the right circle. This blue line is a tangent, it's a common tangent because it's tangent to 2 or more circles. This here on the top here is a common tangent because it's tangent to 2 or more circles. The reason we look at this is so that way we can identify how many we have. So for instance, what if I said draw the common tangents for circles that intersect only once? Now there's 2 different types. Let's draw them. By the way, when I look at this problem, I knew to draw right away because it didn't give me a picture. Most of the time, either A, they'll give you a picture, use it. Or B, they didn't give you a picture, draw one. That's geometry. So I need a circle that intersects only once. The first one that comes to my mind is one like this. The other one that comes to my mind is something like this. Forgive me for my crude circles here. Yeah, forgive me for my poorly drawn circles. But now they want me to draw the common tangents for both cases because these are the 2 different types of circles that will intersect only once. So, well, I see one that goes across the top here. This would be one common tangent if it goes across the top. Now, if you're not very good at drawing, make sure the dot includes that it is a tangent. Well, if there's one across the top, I bet there's one across the bottom. Well, any I draw over here won't even touch the circle. Same thing over here. No. Oh, wait a second. There's one straight down the middle. So this will also be another common tangent. So this one has 3. For the other part of this problem, this one, I could try drawing any on the inside here, but it's going to be a secant for the big one if I draw it any other spot than this one. So this one has only 1. So, it asked me to draw the common tangents for circles that intersect only once. First thing I'm going to do is draw the cases of circles intersecting only once. Then I'm going to draw the common tangents. It's either 1 or 3, depending on what type of circles we draw. Concept 4. This is where we start getting into a little bit more difficult questions. Instead of which ones are common tangents, what does it mean to be a common tangent, what shape art am I dealing with? Now we're going to take it a step higher. And we're going to talk about how the tangent, line, segment, ray interacts with the radius of a circle. If I draw a radius of a circle like I did on this picture here, and I draw a tangent, Theorem 10.1 says that that tangent has to be perpendicular to that radius. If it is, then it is a tangent line. If it isn't, that line there has to be a secant or something else, or that radius is truly not a radius. So the radius and the tangent have to be perpendicular for both of them to be the radius and the tangent. So for instance, if I drew something like this, and I said this is the center, this here is a tangent line, and I drew a segment right here, and I said, hey, this angle right here is 89 degrees. This is for sure the radius. I can tell you with 100% certainty that this line here is not a tangent. Why? Because that isn't a right angle. So in this case, this isn't a tangent. Because it's not a right angle. So I can use this theorem to verify if a line is a tangent. All I have to do is know if that's the right angle. This might mean I'm using Pythagorean's theorem to determine if it's a right triangle. It might mean I'm taking out a protractor and physically measuring it. There's a few different things that could be happening. I could also find information because I know it's a right angle. If I would draw a segment here, I can make a right triangle. If I add a segment, I might get a right triangle. So let's look at a case of how we're going to use this information that the tangent and a radius have to be perpendicular at the point of tangency. So, determine if, in your picture, if line AB is a tangent. Well, how are you going to do that? Well, first of all, I'm going to redraw the picture. Alright, so that's the picture. I want to know if this segment is truly a tangent. This line at the bottom. Well, I look, C is the center of the circle. 8 here is a radius. Wait, if I'm wondering if this is a tangent line, the real question I'm asking is this a right angle? That's really what I'm asking. So let's look at this. Even though we're dealing with a circle, I know how to figure out if that's a right angle or not. And that's because I'm going to erase the circle from my mind. And I'm going to erase the extra information from my line. And look, I just have a right triangle here. Or I'm basically asking you a chapter 7 question. Is this a right triangle? Now how do I tell if this is a right triangle? Pythagorean's theorem, I have 3 side lengths. So I have to verify if 8 squared plus 15 squared equals 17 squared. If it does, it's a right triangle, AB is a tangent. If false, it's not a right angle, it's not a right triangle, AB is not a tangent. So, I'm testing to see whether or not that is true. 64 plus 225, does that equal 289? Still, it's a question mark. 289, does that equal 289? It is true, which means this is a right angle, which means line AB. Alright, so you might be verifying whether something is a tangent using the idea that a right angle is formed by the radius and the tangent. This is how you would do a problem like this. Example 4 looks at it the opposite way. Instead of trying to determine if it is a right angle or if it is a tangent, now instead we're trying to find something like, hey, what is the radius of the circle? We know that segment AB or line AB is a tangent. So if I know something's a tangent and I'm looking for the radius, well, in this case, this is my radius. They had a segment or line AB at the bottom here, A and B. And they told me a few pieces of information. They told me that the bottom segment here is 48. They told me that this here is the radius, and this outside part is 36. Now, they told me that line AB is a tangent, and I know that this R here is the radius. So I know without a shadow of a doubt that because AB is a tangent, segment AB or line AB is a tangent, and segment AC is a radius, that has to be a right angle. Now, what they're asking me to do is find the value of r. Well, again, even though we're dealing with a circle, we are going to erase the part that isn't necessary for this problem anymore. I don't need to actually be looking at the circle anymore because it's not actually part of the problem. But I do have to be careful about one thing. R is R, the radius. 48 was the bottom length here from A to B. However, R was part of it, 36 was the other part. So this segment over here is R plus 36. Because that would be the full length of the segment. A small part of the segment plus another part of the segment adds up to be the full segment. I'm looking for R. Well, I could try sine, cosine, and tangent, but unfortunately there's too many unknowns. 1, 2. Two sides have unknowns, so Katoa will not find me an angle. The only other trick I can think of is trying a squared plus b squared equals c squared. Well, in this case, a squared would be r squared, b squared would be 48 squared, and c squared would be r plus 36 squared. Now, the left side really isn't too bad. As long as you have a calculator, you can get past it pretty quickly. This side would just be r squared plus 2038. So r squared plus 2304. Sorry, my bad. But the right side is going to require a little bit more work. I'm not just going to say it's r squared plus whatever 36 squared is, because that would be wrong. Because square means I'm multiplying it again. So this really is standing for r plus 36 times r plus 36. Ah, that's not r squared and 36 squared. That's a FOIL problem. First, r squared, r times r. Second, outer, oil. O of oil. R times 36 is plus 36r. Plus, inner. 36 times r is 36r. And last, 36 times 36. This one I might actually need a calculator for. 1296. And the left side just gets recopied down. So, just a reminder, if you see r plus a number, quantity squared, you have to FOIL. If you don't FOIL, big mistake. And now at this point, I want everything on one side. Your next step, just put everything on one side. At least put all the r's on one side. So the first thing I'm going to do is I'm going to subtract r squared from both sides. So I get r squared on one side. 2304 equals, ooh, that cancels out, nice. 72r plus 1296. Oh wait, look, r is by itself over here. I think at this point it might be better to just move 1296 to the other side. So minus 1296. Minus 1296. 72r equals 1008. I believe that is the right number. Good. Divide both sides by 72, and I'm not surprised to find that r is 14. Now, let's see, if I plug 14 back in, what do I get? Well, if I look back at where r is, if this is 14, and this is 14, well, this side becomes 50. 14, 48, 50, that's 7, 24, 25, right triangle multiplied by 2. Yep, I did try and sneak one of these in here, so I knew I did it right. But that's how you do it. First step, set it up as a Pythagorean's theorem. A squared plus b squared equals c squared. For the c squared, FOIL. First, outer, inner, last. Then get all the r squareds on one side. If it cancels out, it's a nice step from there. Put everything on one side, solve for r. If r squareds don't cancel out, you're going to have to do something else like what we do in example 5. Alright, but that's it for example 4. Moving on. Example 5, we take a different perspective. We're no longer looking at the relationship between the tangent being perpendicular to the radius. Now what we're going to look at is two tangents of the same circle. So, concept 4, theorem 10.2. I realize we already had concept 4, but I split it up so that way it'd be easier to tackle it, and that way I'm not trying to throw too many things at one time at you. So in this case, it says tangent segments from a common external point are congruent. So if I have a circle, and I have tangent segments from the same point out here, this segment and that segment have to be congruent. Period. So if this segment and this segment are tangents to the circle, then those two segments have to be the same length. Alright, let's look at the problem we have. It says find the value of x. They give us a picture like this. I really should have said something for sure here, but both of those segments are tangents. So segment AC and segment BC are tangents. It'll be clear, it'll mark it some way like this, or it'll literally say point A and point B are points of tangency, or segment AC and segment BC are tangent segments. It'll literally say it. Alright, so this top one is x squared minus 4x plus 2. This is x squared minus 4x minus 2. And I wrote it down wrong. I want this to be 2x. That's 2x squared. Alright, those two segments are tangents. And they come from point C. Those two lengths have to be equal. They have to be congruent. So I'm going to set them equal to each other. X squared minus 4x plus 2 equals 2x squared minus 4x minus 2. And at this point, first step, get all the x squareds on one side. So I'm going to subtract x squared from both sides. This side cancels out. This side, it becomes x squared minus 4x minus 2. Now I look. The last time the x squareds canceled out. This time it didn't. So let's move everything over to the right side. So add 4x to both sides. I get 2 equals x squared minus 2. Oh, that canceled out. In this case, solve for x squared. If you get either x by itself or you get x squared by itself, when you move all the x's or x squareds over to one side, you want to get that quantity by itself. So I'm going to, instead of subtracting 2 from both sides here, I'm going to add 2. So x squared equals 4. Well, if x squared equals 4, the opposite of squaring is square rooting, so take the square root of both sides. Just, you have to be careful because plus or minus has to be incorporated. So x equals plus or minus 2. I look back at my answer. Does positive 2 work? If I plug 2 in, I get 4 times 2 is 8. Minus 8, I get negative 2 for my answer. Oof. Here, 2 squared, 4, minus 4 times 2 is minus 8. Ooh, I get negative 2 on the top. So in this case, positive 2 is actually an answer that doesn't work because it gets negative length, and it doesn't make sense to make negative length. So I'm hoping that x equals negative 2 is my only answer. Negative 2 squared is going to be positive 4. Minus 4 times negative 2, well, that's plus 8. 4 plus 8 is 12. Plus 2 is 14. Negative 2 squared is 4 times 2 is 8. Plus 8 is 16. Minus 2 is 14. So in this case, my answer was x equals negative 2. Plug them both back in. Make sure you don't get a negative length. One of them probably doesn't work. Both might, but one might not. In this case, it ended up being the negative answer that worked, because it made positive length. Alright, and there we go. I realized at the top I said example 4, but this was example 5. These are the types of problems you'll see in section 1. The ones dealing with concept 4, 2 new theorems. Those are the ones that are for the second day. Those are the ones with the right angle, Pythagorean's theorem. They're a little bit tougher because the algebra is a little bit tougher. But the ideas behind them really aren't that bad. Look for the right triangle. A squared plus b squared equals c squared. Or set them equal to each other and solve. Those ideas aren't bad. It's just the algebra here that we add up a little bit level of difficulty. But that's all I have. Till next time.